Students, we are talking about mean temperature difference or mean temperature. Okay, this is the mean temperature at which the whole fluid can assume to be acting on, because temperature varies along the whole thing, right? Along the whole cross section, the temperature varies. So what is the mean? It is equivalent to having continuity equation. In continuity equation, what do you say in pipe? You say A1 V1 is equal to A2 V2. What is this V1 and V2? At which location it is? It is the average. So V1 is actually Q by A1, is it not? And V2 is equal to Q by A2. Make sense? So Q, what is Q? Q is nothing but integration of U, which is a function of R, into 2 pi R dr. Or in the other way around, I can say U into dA. It is a general. Across the area of cross section, U into dA across A1, this is the case. Makes sense. U is varying all the through. So that U variation, when you take it, you get the average. Similar way, this temperature has been obtained. Mean temperature has been obtained. I hope that is clear to you, students. Now, sometimes instead of using the mean temperature, we use something called bulk mean temperature. Bulk means almost. Okay. Sometimes, okay. Generally, generally, for ease of calculation, ease of calculation, the fluid properties are usually usually evaluated evaluated at the bulk mean fluid temperature, at the bulk mean fluid temperature, bulk mean fluid temperature, which is which is bulk mean fluid temperature. I'll call it as TB, which is the which is the arithmetic average arithmetic average average of the mean temperatures of mean temperature at the inlet and outlet. Now, why this is done? Because temperature does not remain same of the pipe. Now, if I do everything, T mean varies, is it not? Here T mean is different. Heat transfer is happening. T mean is different over here, is it not? So this is Tm1. Yeah, I'll say it is Ti, T mean at I, and this is T mean at outlet, if I say so. Or this I can also write Ti. This is equal to To, mean temperature at the inlet and mean temperature at the outlet. So instead of taking the whole thing, you take outlet of the pipe, right? So that is TB, T bulk mean. Okay, TB is equal to Ti minus T exit T naught divided by. Actually, it is very difficult to do it. You understand? This one here there is a different temperature profiles as there is heat transfer which is happening. Here the temperature profile will be different. So to take the whole thing, it becomes so difficult. So for ease of calculation, we take from inlet to outlet, the arithmetic mean. Makes sense? And most of the case, it becomes almost similar. You don't have to worry about it. The error is very less. Okay, so this is how it is taken. Okay, next one. Reynolds number, so entrance region is one thing which is very very important. Okay, so another one is the entrance region which we have done already. So I will run through it. Okay, I'll run through it and I will give you very important points. Okay, some mathematical points I will tell you, which concepts you always know it. Okay, but that is very important to understand. Okay, then we will go with constant surface heat flux, and yeah, and here log mean temperature difference, LMTD, which we will be using in heat exchanger, that we will understand today. You have to understand here this LMTD I'm doing here, that is same as our heat exchanger. And this for pipe convection problems is very less. One or two has come. One on bulk mean temperature calculation, it has come. Okay, but when you consider our LMTD, it has come a lot. Heat exchanger design, a lot of things have come on that. Okay, almost every two question papers, one question will be there. Okay, so it's very important, heat exchangers. Okay, so now let us go with entrance region. Entrance region, very important. The entrance region, the entrance. Let it be capital because it's entrance. Generally, what happens? The fluid flow which is coming inside the pipe. We know that this fluid flow inside the pipe. I'm not putting the cross section because cross section can also be circular, square, triangular, any cross section it can have. If I put it like this, then it means only circular. Okay, it can have any cross sections. Okay, so it can be triangular cross section also. So you may have it, instead of writing like this, you can write this way. This would be the triangular cross section. You may have a square cross section. You may have a square cross section. You may have a circular cross section. It may be any cross section which is there, right? So that has to be kept in mind before. When I draw this, don't keep in mind it's plates. Those are not plates. Those are ducts. Okay. So if you go in the duct, what happens? The flow which is there, say uniform flow, enters, right? And now when it enters here, the effect of viscosity comes into picture. And there is an acceleration. There is retardation near and there is acceleration at the center, is it not? You see this length and this length. This length is bigger than the center of this. So make uh, write it just such a way that this length is smaller, this length is bigger. It's slightly bigger, but that acceleration has to be seen because it is retarding here. Same Q is going inside. So if it is retarding at one place, it has to accelerate at the other place. Getting the point? So it is retarding here, but whereas accelerating here. Okay? And slowly, what happens? This boundary layer will be such that it will go like this. So it will go this way. It will go this way. This is over here. Keep in mind, this is over here. That's why you see this coming over down here. And this would be the this would be the way the boundary layer develops. Is it not? And this length which is there here, it is much higher. So we have to keep in mind that it may come like this and write it in such a way that I have seen in and make it symmetrical. Okay, this is much bigger and this is much bigger, right? And this should be bigger, very big. because it is accelerating. Makes sense? It accelerates at the center. Now, this is called a fully developed profile. This is called the fully developed profile, and this is developing profile. This is developing profile anywhere at the end. Okay, this here from here to here is called the irrotational core. There's no rotation there. That's called irrotational core. The region in the pipe flow, the irrotational core is found in developing region. So if you say here on from here to here, this is called developing region, or it is also called hydrodynamic entrance length or developing length. And from here onwards, it is called developed length. It is developed length, or it is also called or hydrodynamic entrance region. You write region, and this is hydrodynamically fully developed region. This is called hydrodynamically fully developed region. Correct. Hydrodynamically fully developed region. So this thermal entry length, you can write it as sorry, not thermal. Hydrodynamic entry length is written as L only. Hydrodynamic entry length. Okay, there is no number which is given. We can give it. We can have not give it. No problem. Okay. So when similarly we have thermal entry length. How it is about thermal entry length? Thermal entry length I will write here only. So you can write next to that. This is hydrodynamic. Hydrodynamic. Okay, let it be. This is hydrodynamic. Thermal, when you see, you will have. Yeah, the book continue. ಇದು ಅನ್ನೋದು ಯಾವ ಪ್ರಾಬ್ಲಮ್ ಪ್ರಾಬ್ಲಮ್ ಇರುತ್ತಾ ಅದೊಂದು ಉಂಟು ಮತ್ತೆ ನಿಮ್ಮ ರೆಗ್ಯುಲರ್ ಗೇಟ್ ಇದು ಈ ಬುಕ್ ಇಂಥ ಬುಕ್ ಮ್ಯಾಥ್ಸ್ ಉಂಟು ಅದರಲ್ಲ ಎಲ್ಲಿ ಉಂಟು ಸಿವಿಲ್ ಇದರಲ್ಲಿ ಉಂಟು ಅದೇ ಉಂಟು ಪಿ ಎಸ್ ಎನ್ ಅಲ್ಲೂ ಉಂಟು ಪಿ ಎಸ್ ಎನ್ ಬುಕ್ ತಗೊಳ್ಳಿ ಅದರಲ್ಲಿ ಉಂಟು ಮ್ಯಾಥ್ಸ್ ಉಂಟು ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಉಂಟು ಸಾರಿ ಪಿ ಎಸ್ ಎನ್ ಅಲ್ಲಿ ಉಂಟು ಹೌದು ಪಿ ಎಸ್ ಎನ್ ಅಲ್ಲಿ ಉಂಟು ಒಳ್ಳೆ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಆದರೆ ಸ್ವಲ್ಪ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಇರುತ್ತೆ ನಾವು ಕೊಡುವಂಥ ಎಕ್ಸ್ಪ್ಲನೇಷನ್ ಅಲ್ಲಿ ಇಲ್ಲ ಸ್ವಲ್ಪ ಕಮ್ಮಿ ಇರುತ್ತೆ ಸರಿ ಈಗ whenever a student takes textbooks I feel very happy because the original one is there but then when you take textbooks I have to be more prepared. You understand? I have to be more prepared. That's correct. Okay? But then that is good because when I am more prepared, whichever mistakes I do will be caught by you easily. That's how it should be. Okay? So I am very happy when you take a textbook and read. Not that easy. Okay. Chalo. Now, here, when you say thermal boundary layer, what's going to happen? This is the temperature profile which is there. This is the T entrance. At the entrance, you will have the same temperature everywhere. Incoming flow has the same temperature. But as it goes, the temperature increases. It goes to T surface. See, this is Ti. Now T surface, this is Ti. Okay, it's same. T surface may be greater or lesser. We don't know. You understand? This surface, this fluid will instantly get the temperature T surface or T wall. It will instantly get. But further, it may not have. So what will happen? It will happen like this. And this will be at, so let us say this is the axis. Okay. This region, irrotational region, okay, may not be totally having the same temperature. This is Ti. It remains Ti. And here, this one is the thermal boundary layer, which is somewhere here, starts over here. Correct? This is the thermal boundary layer here. Make sense? And this would be the thermal boundary layer. Make sense? This would be the thermal boundary layer, right? Make sense? That would be the thermal boundary layer. Not straight, it is curved. Ti, that is initial temperature. Which one? This one is hydrodynamic. This is velocity. This is velocity. This is the temperature. So what is this? This is the thermal boundary layer. Very important. This is the thermal boundary layer. And this is the velocity boundary layer. So we have both thermal boundary layer, thermally developing length, and hydrodynamically developed length. So whatever is there below, before this, before developed region, you will have at the developed region how it will be. Okay, I have to make this a bit smaller. So that developed, I have to accelerate the development. Okay, so I'll write it better, students. Okay, so let us accelerate the development, and here also we'll let us accelerate the development. Okay, so I'll say developed here. Okay, in your book you can do anyhow because you know what is the space there. Okay, so this one after this, how the profile would be? Profile would be like this. It will be bigger, of course. This is the region which has a hot fluid, cold uh, pipe wall. Okay, so this is the temperature. Yes, please. Yeah, it will be inside. Inside this, the wall will be bigger. Make sense? But then there it will be like this. It will go like this. Then it will go this way. Initial. And as it develops, the whole region goes parabolic. I hope you can make that out. Is it not? So very simple this is. Okay. So here, this is called thermal entrance length. This is called the thermal entrance length or entrance region, and this is thermally fully developed region. This is thermally fully developed region in pipe. Very important to understand this. Now, how do you define it mathematically is important. Writing is okay. Mathematically, how do you define? Okay. Uh, okay. Right in the next slide, you just understand things. You don't have to write in the same thing. You can write in the next slide, next one also. Don't save space. If written just like I have written, okay, it's okay. Sometimes you have to, you call that, there's a specific word. It's not copy. You have to give copy with the very some imitate. If you say you copy it, then it is a different thing. You say imitation, is okay. Or imitating it. Okay, that's fine. Okay. So initial learning is by imitation only, is it not? The actual learning comes later. I also imitate a lot. Okay, so I cannot blame anybody for imitation. But the higher learning is going one step higher than that. Okay, may not be comfortable to a lot of people. Okay, it's not comfortable. There's an easier path of going. Okay, sure. Now, a region is hydrodynamically hydrodynamically fully developed fully developed when dou of u of r comma x divided by dou x is equal to 0 as u is equal to u of r, and it is thermally fully developed when dou by dou x of t wall of x minus t of r comma x divided by t wall of x minus t mean of x is equal to 0. See, we are talking about t mean. We are not talking about which one. We don't have anything to have. We don't have t infinity here. Observe the difference. Okay, that is very important. Okay, makes sense. Next point. See, always in thermal boundary, in velocity boundary layer or pipe flow, what is more important for us? Wall shear stress. Agreed? So, have you written this down, everyone? In in uh, for sorry, I'll call it for velocity profile, or for flow of water, flow of for hydrodynamic consideration, consideration, consideration. Now, I've told you two things which are important. Initially, I said, what are the two things? One is pressure drop, another one is heat transfer. These two, right? For hydrodynamic consideration, pressure drop is an important factor. Or from I'll write, this is better. From, don't write students. From hydrodynamic consideration, pressure drop is an important factor. Correct? Pressure drop is an important factor in this one. Pressure drop, pressure drop is related to wall shear stress. Correct? Pressure drop is related to wall shear stress. Now, wall shear stress, this is like Abdul Kalam's speech. Okay, Abdul Kalam says, family is the main thing. Okay, if family is good, the community is good. If the community is good, the nation is good. So here, similar way, the hydrodynamic consideration, pressure drop is an important factor. You need pressure drop. If you want pressure drop, you need pressure wall shear stress. If you want wall shear stress, what do you need? Wall shear stress calculation considers velocity gradient at the wall. Correct? Velocity gradient at the wall. Or for developing region, developing region, du by dr at r is equal to r. That is at the wall. R at wall. I'll say at wall. At wall. Okay? At wall. Make sense? What happened? What's the problem? Right? Du by dr at wall. What happened? Anything funny? Please tell me if it is funny also. Okay. So du by dr at wall, du by dr at wall for developing region, du by dr at wall is not a constant, not a constant, and hence, and hence, tau w is not constant, not constant, and pressure drop, tau w is not constant. Also, the friction factor, very important when we do it, friction factor. What is friction factor? Friction factor is tau w, F is equal to CF, friction factor. CF, we are using Sohm's things. Okay, Sohm's notations we are using now because we are comfortable with Sohm's notation. Is it not? I don't know. I am comfortable. Okay, CF is equal to not friction factor, coefficient of friction. We will not talk about. Also, the coefficient of friction given as CF or small f is equal to tau w by half rho u infinity square. Here what you say? Rho u average square. Because that remains same all through. Is it not? Rho infinity is rho average. U average. U infinity is U average. Is it not? Also the changes. Changes. But for developed flow, write it down. Write it down. But for developed flow, tau w du tau w and cf is constant because because dou u by dou r at wall is equal to constant. Because here you see it is continuously changing. Du by dy is continuously changing. Here it is more steeper, here it is less steeper. So what is more here? Whether friction factor or the coefficient of friction is more here, and it goes further and further, it reduces. Make sense? So if you consider here, I'll put the graph later on. Okay. Yeah, write this down. Very, very important. This can be asked. Not asked till now, but we don't know. It may be asked this time. And because I have told, okay, so be because this is a basic question that they can ask, not being asked. That's it. But the probability of asking is huge. Fine. Now, how will the variation be? The variation depends on, so I'll write both the variation here only. This is length, okay, this is the length, and this is F, that is CF, equivalent to CF is in heat transfer or HF. Heat transfer coefficient, is it not? Heat transfer, H, heat transfer coefficient. So it may so happen that heat transfer coefficient also drops if it is a thermal boundary layer. This is thermal developing length. And if it is hydrodynamic boundary layer length, it is like this, and then we go like this. Scales may be different, okay? This is H variation, this is CF variation. So is this one is called hydrodynamic length. This is hydrodynamic entrance length. This is hydrodynamic entrance length. This one is the thermal entrance length. Afterwards, after it comes as a this one, it is almost the same. There is no variation in the thermal bond, the heat transfer coefficient, or the coefficient of friction, source friction factor. Pressure drop. Pressure drop is more in the developing region. Pressure drop is less in the is not there in the pressure variation in the pressure. The variation in the pressure drop. Pressure drop is constant in the developed region. Pressure drop continuously reduces in the developing region. Heat transfer is more in the developing region. Okay, now the question is, sir, can't we keep only developing regions? We can try. We can try because developing region has a lot of understand. So what is that? Shear layers are more. That's a shear layer. When more shear layers are there, there's more heat transfer. What do? They put fins inside. Wherever heat transfer is required. Inside the this one not fins. You call it's not called fins. It is called fins for a different region. Those are called vortex generators. So shear layers are generated inside or outside. Heat transfer can happen both sides. So if you have a pipe like this, say this is a pipe. This is a pipe here. What do? If there is heat transfer which is happening across the pipe here? What they put? They put some how to say? They put some wings there. Okay. So when you have wings, there is vortex which is generated, which for the pipe later on, which is coming here, the later on pipes, it will increase the heat transfer rate. Okay, so in heat exchanger, what do you want? You want heat transfer rates to be changed. So these are the passive things. But then when you have this, what happens? Pressure drop increases. It's always a play between pressure drop and heat transfer. So pressure drop more means more pumping power. So it's all economy that matters. You put more obstructions, more pressure drops. Heat transfer rate increases, of course. But then what is the heat transfer rate you are achieving? What is the economic benefits you are achieving because of heat transfer increase? And what is the degradation of economy, or what do you call, not degradation of economy, that's big thing, okay? So how much loss you are going to have, or how much you're going to spend for that pressure drop. So there you have an optimum. So that optimization is done. Make sense? So engineering is all about optimization. Engineering is all about being the best economically. Economics and engineering goes close by. Every design consideration has a lot of things. Then what is the other consideration? Manufacturing. What would be the manufacturing cost here? If I want to weld that, what is the cost involved? What is the in the sense the fixed cost which I incur, and what is the recurring cost that comes out of it. Recurring cost is the pressure drop. Because of the pressure drop, more power being generated, power requirement for making that in the heat exchanger. So you have to get the optimum, the best one. So optimization is something which is very common in any engineering. You cannot live without optimization. This is also the pre-log for next one, industrial engineering we are going for. Next we go for industrial engineering. This is the pre-log. So there we will talk about break even. There we will talk about economic order quantity. Okay, which is very easy and very practical, and you get the best jobs there, provided you know these things. Now there are, because there is a lot best jobs they get, there are a lot of people going there only. It's like computer science. Just because your computer science is giving you a job, everybody is going there. There's no people who are doing that, and everybody can do computer science. Similarly, this can be done by everyone. When you can do heat transfer, you can study to this level of complication. That complication is nothing. Getting the point. So it's added advantage for you. And you say, I know that also. You are all rounder. All rounder is always preferred. Listen. So India went to New Zealand, is it not? So our bowling depth is very less. So what should happen? A batsman should learn bowling.
Captainship are all.
Huh?
The captain is all.
Captain is all rounder, yes. Not always. Okay. There are sometimes batsmen who are captain, but still. Captain can be all rounder, is it not? Okay. Chal. Then is that clear? Okay. Because he stays in the team for the longest time, is it not? No.
That pipes you have applied to cool down the.
It may be cooling down, it may be heating up. There are a number of things. Like if you have a nuclear power plants, in nuclear power plants, what happens? First of all, there is these things going wherever the nuclear reaction is happening. This hard water goes up, and it increases the temperature. Then there is heat exchanger, exchanging heat between hard water and soft water. And this soft water runs the turbines. So what is happening? One is heating the other. Heat transfer rate has to be more. You understand? That's it. So this is very not that difficult. It's easy. Okay.
So what do you mean? How to delay the this one developing region? How to increase the developing region?
How to increase the developing region? Smooth pipes. If you have a smooth pipes, developing regions are delayed, is it not? If you have a rough pipe, developing region comes first.
It is turbulent mode, right?
Turbulent more.
Faster rate.
Yes. Faster rate it will go. Okay, so let us see that. Okay. Or maybe we will have the things here. It depends. A lot of things. Okay. And also it depends on the velocity also. Velocity is more, the incoming velocity is more, developing region is big. Why? Because at any point velocity is more, the boundary layer thickness is less. When the velocity is more, boundary layer thickness is less. So when velocity is more, entry length is more. When velocity is less, entry length is less. Yes or no? And velocity is more, h is more. This will start somewhere here. H when velocity is more. F also similar way. Or F goes down. How is it? CF is related to Reynolds number. And Reynolds number comes in the denominator. So F is reduced. What is CF? 1.3, 0.332 into, come on. I can forget, you cannot. Or you must not. Root of REL, is it not? REX. So root, as velocity increases, CF decreases. What about heat transfer? Same thing with the heat transfer. Heat transfer also same thing, is it not? It is root of Rex actually. As velocity increases, heat transfer rate increases. No, other way around, yes. Heat transfer rate increases. Whereas coefficient of friction reduces. Everything is in the formulas. Make sense? Chalo. But give some time, students, for this. It's not that easy. It is counterintuitive. A lot of things are counterintuitive. You have to spend time on this. Spend time before gate, not during gate exam. You cannot. If you start thinking here 15 minutes is gone. 15 minutes you can do a lot of things. You have to think about this prior to gate. We have around 70 days now. In this time only you have to think. Not wait later on, is it not? Yeah. Next. Yeah, December, January, very close, very close. Dak tak. ये dak tak is coming. धक धक करने लगा. Huh? For smooth pipe, what happens? What is the boundary layer thickness for smooth pipe? Lesser, right? So developing length will be more. For higher velocity boundary layer, for higher velocity, will the boundary layer bigger or smaller? Smaller. So developing length is high. What is this boundary layer thickness? This is boundary layer thickness. If boundary layer thickness is small, then what happens? Developing length will be high, is it not? Developing length is this length. If boundary layer is small, when the velocity increases, this goes like this. And the developing length, it meets over here. These two boundary layers meets at a lot higher, more distance. Is it not? At a higher distance it meets. The developing length will increase, is it not? Person is farting like anything. The farting bikes. Okay. It's a nuisance. Come on. Okay. People should not create nuisance. Correct. Chalo, done.
So that way turbulence also can be delayed if developing like turbulence.
Turbulency. Incoming flow also can be turbulent only.
The starting only.
At starting only it can be turbulent flows. It can be turbulent developing length. What is this? This may be the mean velocity. So it can be anything. Okay. So we don't know. Okay. And it is still more complicated. You'll understand when you go to thermal engineering, you'll understand how complicated these things are. Convection heat transfer is not that easy. It's not that easy. It's much more involved. Okay. Shallow. Next. Have you written this down, students? Now, what about in the case of, yeah, I hope you get the point, students. Okay. So, so in the developing region, in the developed region, in the developed region, dou by dou r of T wall minus T, the local temperature, divided by T of wall, T of, I'm not writing X here, observe. This is the T mean, no, minus Tm, T mean. This is T, local temperature at that position. Okay. At any R is equal to R. At R is equal to R. It is the boundary. Is equal to minus dou T temperature by dou R at R is equal to R divided by T wall minus T mean at that particular location. T mean does not mean Ti and To. Bulk mean temperature is taken by Ti and To. Ti varies as it goes through the pipe. This understanding has to happen. Ti varies as it goes through the pipe. Ti is the average velocity in average temperature. Velocity remains same. Velocity, whatever the average velocity is there, from the starting till the end, it remains same. Why? A1 V1 is equal to A2 V2. Temperature is not that case. So complications on the temperature. Mean temperature changes. Why? There is heat transfer. It is like some part of what to say, water being dripping out. If it is insulated, it remains the same, of course. If it is insulated, it remains the same. Very good. If it is insulated, it's adiabatic pipe. Yeah, T mean is same. Ti is equal to T out. Yes. Because there's no way energy can go out. Is it not? So Ti is equal to T not in case of insulator. Correct. So that is how you have to think. Okay. And this is not a function of x, not f of x. Is not a function of x in the developed region. Very important. And q dot q dot at wall is equal to hx, h at x into t wall minus t mean, t wall minus t mean. That is the difference, which is given as k into dou t by dou r at r is equal to r. Very important, used in lot of problem solving. Gate, there are limited questions on this, but this is important in understanding. Otherwise, just because in gate the questions have not come, why do we stop understanding a concept, which is so important, which is essential concept? And not that it is not there in the gate syllabus. Just because it has not been asked frequently does not mean it will not be asked this time. We have to preempt. We must not react. What most of the people are doing is, what gate previous questions comes, based on that we decide what question will come this time. It may not repeat. Okay. We read essentially to understand. That's it. Okay. So done. So now hx can be equal to k times dou t by dou r at r is equal to r divided by tw minus tm. There has been one question on this. There has been one question on this. Tw minus t mean, yeah, minus t. This is when tw is greater than t mean. If tw is lesser than t mean, this is tw to t mean, right? So higher to lower. So when it is higher to lower, this can be plus. From higher to lower, it can be plus. So this is plus because dt is negative.
That negative depends on that dt by dr.
Yeah, dt by dt. It is negative. Obviously, it is negative. As it goes to the.
So that k should be negative.
Okay, that would be better because, yeah, but why did he not take like this t surface t mean to, where is the heat transfer happening if it is positive? T mean to T surface, T wall. T wall is less, yes. So let me write this as negative. Wait a minute. Let me make it proper, negative, and let me write this as T mean to T wall. Let negative be there. Then let me write T mean minus T. Problem solved. Sorry. ಎಲ್ರದಾಯ್ತಾ ಬರ್ದು Next. Next, let us see entry lengths, what is taken in general. Okay, this is the one which is done. Okay, in general. Okay, in general. Okay, in general. Because of Shah and Bhatti, I don't know whether he was Jispal Bhatti or not. Okay, there was one person called Bhatti. Okay, I'll see. 1987, he has given a paper based on that. Okay, these are something which we are discussing. The recent one, 1980s are recent, is it not? You know, this 1987 Bhatti. Yeah, MS Bhatti is not this one. Turbulent and transition flow in convective heat transfer in ducts. Okay. Wiley interscience. So there's a lot of things happening. Indians are also involved in number of things. Shah also is there. He is not Amit Shah, but mean temperature is the mean temperature at a cross section. This one. This is equivalent to this. If I see.
Not the maximum.
No, it's a mean. You calculate that using this equation. It is just like I said. See here is mean average. What is this V1? V1 is average velocity. If the whole cross section would have the same velocity, area into velocity will give that Q. T mean implies if the whole thing would have been a T mean, then it would have the same energy flow rate. Make sense? So what is happening? Integration of Cp, Tr, dm dot.
Case of hot fluid and cold surface. Mean will be
We are not worried about cold and heat, hot surface. We are talking about fluid temperature. We are talking about fluid temperature. Fluid temperature, see here, this is cold fluid and hot wall. T mean may be somewhere here. Here, T mean will be somewhere here. It is a calculated one. It is not the actual one. It is for the ease of calculation.
then TB is
TB is about the Ti here, that is T mean at inlet. This is T mean at outlet. Now this and this, now properties changes with temperature. So at which temperature should I take the properties of the fluid? I should take at bulk mean temperature, which is the mean of the inlet and outlet mean temperature. Okay. Then you calculate and then you do. There is errors, but the errors are negligible.
only the negative way.
Which one? I'm not. Oh, sorry. Correct it. Sorry. Add it fast. Big mistake. Big mistake. It's arithmetic average. Arithmetic average is Ti plus Tb divided by 2. Mistake. You cannot negate it. It should be Ti plus Tb by 2. Correct. Thanks, Agastya. I think when you saw that there was a Kida, I don't know where to correct it. So, fine. Chalo. Any doubts, students here? It's clear. Very important these are. Okay, that's why I'm going slow also. This is useful in our this is useful in LMTD, heat exchanger design. Okay, so there we will see. This understanding is important. Okay, now entry length has been calculated by Shah and Bhatti as well as Case and Crawford. Okay, L hydrodynamic for laminar is given as almost equal to 0.05 Reynolds number into hydraulic diameter. You know what is hydraulic diameter, is it not? If it is duct is not circular, but it is having other cross section, you take hydraulic diameter where DH is equal to 4a by p. You take height. This is what we did in Reynolds number also, is it not? Same thing we are going to do this. Okay. So next, or is it a by 4p or 4a by p? You can calculate how, you can say 4 into pi r square divided by 2 pi r. So what you get? R cancels. So 2 pi r, right? No, 2 pi r. Okay. So this is 2. So you get 2 pi r. No, 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 no. If you 2r you get, yes. You get 2r. So fine, correct. 2r is one diameter. Correct. So this is correct. So sometimes I get into confusion. When I get into confusion, I resolve like this. Okay. And L, this is what? This is hydrodynamic entrance length approximation by Shah and Bhatti. Shah and Bhatti. Our Jaspal Bhatti was also doing this research. It was in chemistry. Okay. You know our Jaspal Bhatti from Jaspal Bhatti, is it not? No. Come on, he is a great comedian. Before Kapil Sharma, he was a comedian. He used to do small. Okay, fine. Then thermal entrance length approximation is also given as LT. Laminar, very important. Turbulent is different. Laminar is almost equal to 0.05 RE PR into DH, which is actually equal to Prandtl number into LH laminar. This is important. This is important. This can be asked. They might say that thermal boundary layer thickness is so, thermal entry length is so and so. What is the hydrodynamic boundary layer? Given the Prandtl number. Questions have not appeared till now. This time it may appear. It's a possibility. So we have to be very careful. We have to preempt what kind of question they may come. They will say in a particular flow involving fluid with viscosity so and so. This one to say heat transfer coefficient Cp, or they may give the heat specific heat Cp, and then conductivity K. Okay, the thermal laminar boundary layer, laminar entry length was found to be 5 centimeter. What is the turbulent entry length? Whatever 5 centimeter is there, you have to multiply by Prandtl length, Prandtl number. Then you will get the thermal boundary layer, thermal entrance length. Let us do one problem just like that to say that it is being done. Okay, so that you could get it. Okay, and for turbulent, let me tell you, for turbulent, L H for turbulent is almost equal to L L for turbulent, LT for turbulent is almost equal to 10 times D. 10 times the diameter, it generally becomes, it is the entry length for turbulent. Okay. This is what is seen from a lot of experiments. Okay. Let us do one problem, preempt problem. Okay, I don't know whether it has come, but it may come. Okay. So if preempt comes, tell me. Okay, because after gate is over, I will never see the question paper. I think lot of my students also do the same thing. After gate exam, they will not do how to say dissection or post-mortem of that. Done is done, sir. Enough, sir. Before that, whatever we do it. Now it is done. Whatever happens, happens. Next time we'll prepare. Why to do that? So I also don't disturb my students during that time. But I say come to the classes. ಟೆನ್ಷನ್ ಆಗ್ತದೆ. ನಾನು ಗೇಟ್ ಆದ್ಮೇಲೆ ಯಾವತ್ತೂ ಕ್ವಶನ್ಸ್ ಕೇಳೋದಿಲ್ಲ. ಗೇಟ್ ಪೇಪರ್ ಏನ್ ಬಂತು ಅಂತ ಕೇಳ್ತೇನೆ ಅಷ್ಟೇ, ಎಷ್ಟು ಬರ್ಬೋದು ಅಂತ ಕೇಳ್ತೇನೆ. ಅದು ಯಾವ್ದಾದ್ರು ಬಂತು ಇದು ಬಂತು ಯಾಕೆ ಸುಮ್ಮನೆ ಬಿಡಿಯಪ್ಪ, ಇಷ್ಟು ಟೆನ್ಷನ್ ತಗೊಂಡಿದ್ದೀರಾ. ಗೇಟ್ ಆದ್ಮೇಲೆ ಸ್ವಲ್ಪ ಆರಾಮ್ ಮಾಡಿ, ಒಂದು ವಾರ ಮತ್ತೆ ಕ್ಲಾಸಸ್ ಒಂದೇ ವಾರ ಆಯ್ತಾ, ಅದಾದ್ಮೇಲೆ ಕ್ಲಾಸಸ್ ಅಟೆಂಡ್ ಮಾಡಿ. ಯಾಕಂತ ಹೇಳಿದ್ರೆ ನೆಕ್ಸ್ಟ್ ಇಂಪಾರ್ಟೆನ್ಸ್ ಇದೆ. ಈಗ ಆಗಿದ್ದಾಯ್ತು, ಏನ್ ಮಾಡಕ್ಕಾಗುತ್ತೆ. ಕ್ವಶನ್ ಪೇಪರ್ ಬರ್ಲಿ, ಕ್ವಶನ್ ಪೇಪರ್ ಬಂದ ಮೇಲೆ ಆನ್ಸರ್ ಕರೆಕ್ಷನ್ಸ್ ಅದೇ ಆನ್ಸರ್ ಮಾಡಿದಿರಾ ಇಲ್ಲ ಅಂತ ಬರ್ತದೆ ನಿಮಗೆ. ಒಂದ್ 2 ದಿನದಲ್ಲಿ 3 ದಿನದಲ್ಲಿ ಬರ್ತದೆ ಅಲ್ವಾ. ಆ 3 ದಿನ ನಂತರ ಆಫ್ಟರ್ 3 days you see whether you have given the same option, the things has come proper or not. Such kind of things you do. That's, and maybe to challenge later on. Okay, that you can. But those people do a lot of about this. We don't have to worry about it. This 90,000, 95,000 people are doing, and people are much more serious than us. Okay, so they'll do it. So we don't have to worry about it. Okay, so we can be around say next whatever the uh, goal is there, on that we can concentrate. Okay? Which is getting a job or getting a JR based on our performance. Once we come out, we know within 2 to 3 days we will at least know how was our performance. Based on our performance, we will prepare for the next point. ಆಗಿದ್ದು ಆಗೋಯ್ತು, ನೆಕ್ಸ್ಟ್ ಏನ್ ಮಾಡ್ಬೇಕು ಅಂತ ನೋಡ್ಬೇಕು ಅಷ್ಟೇ. ಈಗಲೂ ಹಾಗೆ, ಈಗ ನಮ್ಮ ಕೈಯಲ್ಲಿದೆ. ನಾವು ವಿ ಹ್ಯಾವ್ ಇಟ್ ಇನ್ ಅವರ್ ಹ್ಯಾಂಡ್. ಟಿಲ್ ಗೇಟ್, ದ ಗೇಟ್ ರಿಸಲ್ಟ್ ಈಸ್ ಇನ್ ಅವರ್ ಹ್ಯಾಂಡ್. ಓಕೆ, ಪುಟ್ ಅವರ್ ಫುಲ್ ಎಫರ್ಟ್ಸ್. ಓಕೆ, ಚಲೋ ನೆಕ್ಸ್ಟ್. Next, okay, so now one more point, let us do the problem. This is preempt problem. Preempt problem. Okay. For a flow involving, for a flow involving flow inside a tube. Okay, flow inside a duct of 3 centimeter diameter, 3 centimeter diameter, and 3 centimeter diameter with a with a liquid flowing with properties say Cp is equal to 4 point, or C is equal to 4.18 kilojoules per kg Kelvin. Mu is equal to 0.0001 pass and 0001 pass and 0.0001. Okay, this is my fluid. I did not say water. Did I say it's water? No, I did not say. Okay, let it be. Okay, 0.01 pass and K is equal to 1 watt per meter Kelvin. Hydrodynamic boundary length, or let us say thermal boundary length, thermal developing length, was found to be 55 centimeters. 55 centimeters. The hydrodynamic boundary length would be the hydrodynamic developing length is developing length in centimeter is dash. Round off to 2 decimals. Density has to be. Density is equal to, you can write here another one. Density is equal to 1000 kg per meter cube. Do you need density here? Density is not required. Leave densities. Yeah, Reynolds number is not required, is it not? Just think about it. One answer. ಬೇಗ ಮಾಡಿ. ಆನ್ಲೈನ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಬಂತ ಆನ್ಸರ್? ನಾನು ನಿಮ್ಮನ್ನು ಮ್ಯೂಟ್ ಮಾಡಿಲ್ಲ ಅಲ್ಲ, ಮಾತಾಡಿ ಮಕ್ಕಳೇ. $131.57. What was the Prandtl number? So Prandtl number was 0.418. So hydrodynamic length, okay, thermal boundary layer length is equal to Prandtl number into hydrodynamic boundary length. What is given is hydrodynamic boundary length. You have to find the thermal boundary length. Not thermal boundary length is given. We have to find hydrodynamic boundary. So hydrodynamic boundary length is equal to thermal boundary length divided by Prandtl. Thermal developing length divided by Prandtl. So it is, Prandtl is 0.418. So it is 55 centimeter divided by 0.418, which gives us 130.658. So 6658. Round up to two decimals. 589, yes.
131.58.
Sorry. Okay, so it is 131.5 centimeters, correct? So this is a preempt question, don't miss that out. Okay, so we'll stop it here, students. Next I have to start a new topic, which I'll take a break now. Okay, so we will do next class tomorrow at 2 o'clock. We'll meet with, no meeting today. It is channel close. Okay, today, yeah, obviously you will not have it. Okay, so we next meeting is at 4 o'clock.